All right, so now let's look at the reactions of alcohols. We don't have too many, but whatever we have is also critical. So the main things that we're going to do is elimination reactions, which is dehydration to form alkenes, substitution reactions to form alkyl halides, tosylations, and oxidations. And we'll talk a little bit about here and there other stuff too. So let's deal with dehydration reactions first. Dehydration reaction means that you're dehydrating something. Loss of water is dehydration. Loss of water, okay, is dehydration. So alcohol group is the one that's going to leave, but it needs a hydrogen. So it will pick up a hydrogen from the adjacent carbon. That's called a 1-2 elimination, alpha beta elimination. It's always a 1-2 elimination. Never, a hydrogen is never on the same carbon as the OH. Okay, so in any case, so this is the kind of alkene you get for the elimination of this alcohol group. So here, this is via E1 mechanism, and that's something that we need to kind of talk about just a little bit. So here I've given you some dehydration reactions of primary, secondary, and tertiary alcohols because we have three kinds of alcohols. So the alcohols themselves are very simple, okay, in the sense that they're all pretty much three carbons, but arranged differently to give you tertiary, primary, secondary, tertiary alcohols. So the alkenes you're getting are also pretty straightforward, all right? The main thing I want to focus on is the reagents that you're using here. So here is concentrated sulfuric acid, and this is at 180 degrees Celsius. Just consider this as like high temperature. This is for primary alcohols. That's the condition it needs. A secondary alcohol needs concentrated sulfuric acid. The temperature now is 100 degrees Celsius. Could be lower also. And then the tertiary alcohols, which can be done at room temperature also. No temperature means room temperature. So looking at the condition, which is the most stressful condition, you don't have to think too hard for this one. The most stressful condition is the one at higher temperature because you have the concentrated sulfuric acid also, and then on top of that you have high temperature. So this is the easiest condition that we have, where you take an alcohol and add a little sulfuric acid and you get your alkene, okay? This kind of a condition is what led scientists to believe that it's an E1 mechanism, okay? Remember, there's E1 and E2 mechanisms. So for alcohols, it's generally considered to be an E1 mechanism, especially in presence of acid, okay? And here, look at all the conditions are acidic conditions. So let's look at how this is working. So this is just a simple dehydration mechanism. It could be for secondary or tertiary, because remember, primary is the hardest one to dehydrate. Primary also dehydrates in just sometimes a little bit different way, okay? So I'm going to do the dehydration mechanism for a secondary alcohol. So here you can see that the alcohol here in presence of an acid will pick up a proton from the acid, become protonated, and then it will leave, creating a carbocation. That's the E1 mechanism. E1 means carbocation mechanism. So you have to form a carbocation, and then the water comes in, picks up a proton from adjacent to the carbocation, and then you get elimination, okay? So first of all, in acid mechanisms, this step is going to happen, okay, which means the alcohol will get protonated. Okay, now what happens after that protonation is the big thing, right? Because in the case of dehydration, you are actually doing, you're actually forming an alkene, right? So somehow the hydrogen has to go. I mean, water is not the best nucleophile, but in presence of H3O plus, this is actually an okay nucleophile, all right, in order to pick up this proton. The other thing I want to mention here is, since we're talking about a carbocation mechanism, this is a secondary carbocation. So you can see that if it's going to work through a carbocation mechanism, a tertiary carbocation is more stable than secondary than a primary carbocation. So if you're going to favor the mechanism as an E1, then tertiary and secondary carbocations are favored. So primary alcohols will form a primary carbocation, which is not all that stable. Okay, now you can see why, how the mechanism is working, not why. Why is also there. Okay, so once we've understood the mechanism, okay, the mechanism is always going to be like what we just said, okay, where you have the protonation, formation of carbocation, okay, that's going to happen. Now what we're talking about here is what's called regioselectivity. Okay, and this regioselectivity is where is your double bond going to be. In some cases, you don't really have to worry about it. Okay, so for example, the examples I gave you before, you know, where you had the primary alcohol and you had the secondary alcohol, both of them gave you propene. In this case, poor propene has no choice. Either you put the double bond on the left side or the right side, it's the same thing. But when you have larger alcohols, then you can have issues. Okay, when you have secondary, when you have tertiary carbocations, then there is a possibility that you can have more than one product. Okay, why? Let's look at this. So here you have an alcohol that is getting protonated. Okay, so then you lose water. That's the dehydration step. And then you create a carbocation in the process. Now, when you have to do elimination, okay, you have to get a proton from the adjacent carbon. Now, that's called a beta carbon. So alpha is right here where the carbocation is, and then the beta is where you're going to find your proton. So here I've put two protons because these two protons are different. Okay, so that's why I've color coded them so you can see that there is a pink proton and then there is a blue proton. Okay, so here let me remove this so there is a little bit of visuals. Okay, over here. So now you have two beta protons. If you pick up the pink one, then you get the alkene on the terminal carbons. If you pick up the blue proton, okay, which is the second step over here, then you end up getting an alkene that is internal alkene. From the stability of alkenes that you have learned about, you know that internal alkenes are more stable than terminal alkenes. The more substituted an alkene is, the more stable it is going to be. That stable alkene is called Zaitseve's product, and in this case, in the reaction we have just done, that's going to be your major product. Okay, the more stable alkene is going to be the major product, and why shouldn't it be, right? So that's the Zaitseve's product. Now, why did this problem happen? Okay, why did we end up getting two products over here? A Hoffman product, which is the minor product, which is the less stable alkene. And why did we get a major product? We got a major and a minor product because we had two beta protons. Okay, it's not avoidable. Okay, you have two beta protons. Some cases you'll have three beta protons, so you form three products. Okay, so you had two beta products and you don't have any choice. You are going to form two products. Now, which is the major, what's the minor, that you can determine. Okay. All right, let's look at another example, the one below it, and that's a tertiary alcohol. So in this tertiary alcohol, again, you do the same thing, pick up a proton, and then the water leaves. Okay, once the alcohol is protonated, it's a good leaving group. Once it goes away, fine, you create a carbocation. Okay, so instead of writing three reactions, I tried to color code the reactions for you so you can actually see here that you have three beta protons. Okay, so here is a pink proton, that's one beta proton. Then there's a green one. So remember, this is the carbocation right here. So this is the beta carbon, this is the beta carbon, and then here is a beta carbon. Any hydrogen attached to that beta carbon is a beta proton, and that's the one that is able to go. So pink, green, and blue. Okay, so if you take away the pink proton, then you get the double bond on the right hand side. If you take the green one away, which is on the top, then you get this kind of an alkene. The blue one will give you an alkene on this side. Okay, so now you're getting 3 products. Oh my God, this is a mess. Okay, and this is not what should happen in any kind of synthesis. I mean, unless you are studying, the kind of a reaction, that's all. So in some cases that also is valid. But if you're trying to do a synthesis, you should not be getting 3 products because it's such a mess to clean them out and separate everything out. It's a mess. But you got 3 products here. So first of all, let's go ahead and figure out which is going to be the Zaitse's product. Zaitse's products are going to be the internal alkenes, okay, or the more stable alkenes. Here I'm just saying internal because there is such an obvious terminal alkene, okay, the one that's kind of hanging out there. And that's going to be the Hoffman product. I don't like calling anti-Zaitse's. There is nothing like anti-Zaitse's. Okay, there's actually the Hoffman product, which is supposed to be the less stable alkene, is actually a thing. Okay, so Hoffman product is what we're going to call that. And the Zaitse's product is the one that is the internal alkene, which is more stable. Now, in this case, where we have 2 internal alkenes, both of them are actually quite stable. Okay, so you might end up getting both of them almost in equal quantity. Okay, what this shows you over here in this slide is really about the fact that once you generate a carbocation, you are going to get 2 products. Okay, unless you have such a symmetrical kind of an alcohol where you get only one. So like the one that I had before, where there was nothing else going on, right? So if you have something like this, yeah, fine, okay, when you dehydrate that, you will only get cyclohexene, no problem. And really that's what you want to do. You don't really want to get a mixture, okay? But if you do have something asymmetric, then your major product is going to be the Zaitse's product. That's something you need to focus on, okay, over here. Okay, another problem that happens with carbocations, and we've done this before also, is that if you have a carbocation, there's always a chance of rearrangement, okay, in there. So once you form a carbocation, you just kind of have to take a pause and see if you can form a more stable carbocation. All right, so here, let's look at this one. So in this case, the alcohol is getting protonated. The alcohol is leaving as water. So that protonated alcohol is gone. So once that's gone and you create this carbocation, now you have to take a look at this and say, okay, this is a secondary carbocation and I have so many methyl groups on this side. So can I shift one? As yes, you can shift one. Okay, so I wrote over here that rearrangement occurs. You don't have to write it. I wrote it because I need you to remember this. But here you just have to show me a methyl shift going on. Okay, so this is a methyl shift, not a hydride shift. There's no hydrogen there to shift. So you shift the methyl group. Once you shift the methyl group here, okay, so let's say, let me highlight that for you. So if you shift this one methyl group, you can shift any of those 3. They're exactly the same. Okay, so this has shifted here. Now which one is the shifted one? You don't know. But what has happened now is because the methyl group shifted here, you created a vacancy here on that carbon. Okay, so now this carbon is going to get the carbocation. What I'm trying to say here is when you do rearrangements, call it a methyl shift, don't call it a carbocation shift. Okay, methyl is going to shift, the carbocation is going to shift automatically. Okay, but really the methyl group is the one that's doing all the work, okay, of shifting. So anyhow, once that shifts, let me go ahead and erase all of this so that there is no mess. Okay, so now that you have the shifting, okay, that happened, now you've generated a stable carbocation. Okay, this one was a secondary, now this one is a tertiary carbocation. So yes, more stable. Then you look for your beta protons. Okay, so here is a carbon, here is a carbon. Look if there is any proton. Oh yes, there is one here, and then here is another one. Okay, and so you end up getting then 2 products, okay, in this case. So one is a terminal alkene and the other one is an internal alkene. This is going to be your major product. Now, in this case, when you have this kind of a reaction going on, when you have rearrangement going on, the rearrangement is going to happen. Okay, you can't avoid it. Okay, it's going to happen just like you're going to form these 2 products. You can't avoid it. It's going to happen. So which means that with this kind of a reaction, let's say you had this kind of the carbocation. Let me write this again. Okay, so you have this. In this case, there is only one beta proton. Okay, and you say, okay, I'm going to form this product also. Okay, so where you have the water coming in and picking up this proton, and you say, okay, I'm going to get this alkene. No, you will actually never get that alkene. All right, it's not even like a minor product. Okay, because when a rearrangement happens, it's going to happen. Okay, it's not going to leave anything behind, okay, in there. So don't even think about writing this kind of a product. It's not going to happen. All right, now let's look at the primary alcohols. So we looked at the secondary alcohols and the tertiary alcohols. Now for the primary alcohols, it's kind of like an E2 mechanism. It can't be an E1 mechanism, because E1 mechanism means you're creating a carbocation. Carbocations don't form, okay, for primary alcohols, because the primary carbocations are not stable. So you're not going to go through an E1 mechanism. You're going to go through an E2 mechanism. Okay, so for example, if you have something like this, okay, where you have a primary alcohol, do the protonation. Once the protonation happens, this is a leaving group now, right? The H2O, and this is protonated water, sort of. And the water will come in and pick up this proton, and everything is happening at the same time. That's what an E2 mechanism is like, and you get the Hoffman product. Okay, now what happens sometimes in these cases, you don't really get this kind of a product. Okay, the E1 mechanism is preferred in an acidic medium. Okay, so because the E1 mechanism is preferred, you still do the protonation. Okay, but once you do the protonation, what's happening here? The water is leaving. Okay, once the water is leaving, it's not that it's going to generate a carbocation here. At the same time, you get a hydride shift. Okay, that hydride shift happens automatically, and you generate a secondary carbocation. Okay, because a primary carbocation is not forming. Okay, so the hydride shift happens almost as the group is leaving, as the water is leaving. So once you have a secondary carbocation, then you can go ahead again as usual, find your beta protons. Again, I've colored them so you can see the different colors. And so, you get the beta proton. This one is going to give you a Zaitsev product. If you eliminate this one, you end up getting the Hoffman product. Now, if you look at these, both of these reactions, the E2 and the E1, okay, and look at the E2, you're getting one butene. You're getting one butene here also, right? Whether the mechanism is E1 or E2, you're still getting one butene. So one of the ways you can prove what kind of mechanism is happening is actually by doing this reaction. If you get only one butene, then you know the mechanism is E2. But if you also get the 2-butene, you know rearrangement has happened. Okay, right there as the leaving group is going, because you don't generate a primary carbocation. You only generate a secondary one. Okay, so, and this is really what happens. Okay, is that when you do dehydration of primary alcohols, the E1 reaction happens along with the hydride shift. Okay, automatically. So you do end up getting the Zaitsev's product. Okay, so which means that when you're writing this mechanism at any time, do not write that you're forming this carbocation. Once you write this and then you say, okay, I'm going to shift this. No, don't do that. Do everything at the same time, okay? Because a primary carbocation is not going to form. Okay, so that was about dehydration. Now let's talk about substitution with hydrogen halide. So substitution is a very common kind of a reaction that we have done. So for example, if you take an alcohol group and you want to do substitution and you want to make a chloride, the OH, and turn it into a chloride, this reaction does not happen. Okay, so if you write the chloride as like this, which means what? Where is this chloride coming from? A chloride written like this would mean that it is coming from something like sodium chloride or potassium chloride. Well, this kind of chloride is not strong enough to knock this one out, okay, because in substitution, the nucleophile has to be a stronger base than the leaving group. Here the leaving group is OH or OH minus. So the OH minus is not going to be a strong, an OH minus is really a strong nucleophile, and you cannot use chlorine, okay, to take that out, which means this reaction is not going to happen. Okay, so if this reaction is not going to happen, that means we need to find some other way. The other way to do this, okay, is to use an acid. Okay, now we just did dehydration. In dehydration, we were working in an acidic media. So again, we're going to do the same thing. Okay, so instead of just using chloride, we're going to use hydrogen chloride or hydrochloric acid or hydrobromic acid. So in those cases, your mechanism is kind of the same as we did for dehydration, which is that you will take an alcohol, do the protonation, and now once the leaving group goes away, now you created a carbocation. Okay, now because the Cl minus, the chloride from the HCl is present in there, that's going to do the reaction. So it's not an SN2 reaction, it's more like an SN1 mechanism, okay, not SN2. So it's a substitution reaction, but through the generation of carbocation. Why through a carbocation again? Because this is an acidic medium. Okay, so be careful of what kind of a medium you're doing your reaction in. So same problem happens. As soon as you have a carbocation, you have issues. Okay, you don't have it. Molecule has issues. So since this is also an SN1 mechanism, SN1 meaning a carbocation mechanism, a carbocation is going to undergo rearrangement. It's going to happen, okay, whether you like it or not, it's going to happen. So we were just doing this molecule, right? We were treating this with acid to give alkene. Now I'm going to take the same molecule and try to give this kind of a substitution reaction. But if you're thinking that, oh, I can do substitution, it's a secondary alcohol, I just add acid and I will get my chlorine here, I am sorry, that's just not going to work. Okay, so this is not going to work. Why? Because once you do the protonation and the leaving group goes away, you generate the carbocation. That's where the rearrangement occurs. There is a methyl shift. And once that methyl shift occurs, here's your methyl group. And now the carbocation is on the more stable carbon. So this is a tertiary carbocation, this is a secondary carbocation. Now the chlorine can attack here. You will never get any of this product at all. Okay, so you will only get the rearranged product. So is this kind of a reaction useful? Of course it's useful. The only thing you want to do is you want to make sure that you don't use any alcohol which can rearrange. You want to use tertiary alcohols, okay? Tertiary alcohols are fantastic, right? Because you directly form a tertiary carbocation. So, use a tertiary alcohol to do these kind of reactions because, HCl is cheap. So why bother, with issues? Why bother with rearrangements and all that? Start with a substance that you already know is going to give you a good product. But what does it mean for primary and secondary alcohols? Because, okay, fine, with tertiary alcohols, I'll get the product. But what if you do want to get something from a primary alcohol, right? You want to do substitution. So you can't use HCl, right, for primary alcohols because primary alcohols will not form a carbocation. And that's how the HCl works, is through a carbocation mechanism. So if that's not going to work, then you need to use some other reagent. And those other reagents are all right here. Okay, so if you want to get a Cl on there instead of OH, so if you want to substitute with Cl, you use thionyl chloride or phosphorus pentachloride or phosphorus trichloride. That's to get a chlorine on. If you want to get a bromine on there, then you use phosphorus tribromide, PBr3. So this is how you can turn an alcohol into a halide. This is a neat reaction. I've shown you the mechanism, not that you need the mechanism, but right here, this is a mechanism. You get an SN2 kind of a mechanism here. So the only time this mechanism is useful for us is when you're dealing with stereochemistry. For a primary alcohol, you don't have any stereochemistry. But if you do have stereochemistry, then you have to remember that because this is an SN2 mechanism, you're going to get inversion of stereochemistry. Okay, so no matter whether you're doing chlorination or bromination, you will have inversion of stereochemistry because mechanism is SN2. So now we get to tosylates and mesylates. Tosylates and mesylates are really interesting. Okay, so here is the tosyl chloride. Okay, so this is para-toluene sulfonyl chloride. This is a toluene group, and we'll learn about this later on. This is the sulfonyl group, and of course, this is the chlorine. This is the methyl group, this is the sulfonyl group, and this is the chlorine. So there are two kinds of groups here, sulfonyl chlorides. One is a para-toluene, one is methyl. This one is a little bit more preferred in labs because when you work with toluene sulfonyl chloride, you end up getting solids as a result. So it's nice to work with solids because they are crystals, right? And the solids are easier to weigh and transfer and whatnot. So this group is not the tosylate. This is called tosyl chloride, TSCl. Okay. So what happens is you take a tosyl chloride and you can treat that to an alcohol. So, or you can take an alcohol and treat that with tosyl chloride. Once you do that, this whole group is going to attach to the oxygen of the alcohol. Okay, so this is the alcohol. The Cl leaves. Okay, so this is minus HCl, okay, over here, and I can write that in case you wanted, although it's not necessary. So minus HCl, so the chlorine is gone, hydrogen is gone, okay, and then you're left with this whole group that is going to be attached to the oxygen of the alcohol, okay, right here. This is called the tosylate. Okay, this is a tosylate. Now, let me just tell you a little bit about what's going on here. Okay, this whole group that's attached here, this is called the TS group. Okay, so now this is what you have is OTS. Okay, remember this is TSCl. So this group right here is the TS group. This here is the MS group. Okay, this is written just like you would on the periodic table. Okay, like elements. So this tosylate group now is actually an excellent leaving group, okay? And that leaving group can be made to leave by any nucleophile, okay? So you can have even a weak nucleophile come in and then do a substitution. So this is going to be SN2 reaction. So inversion of stereochemistry occurs, and then you get an SN2 reaction here, okay? Substitution reactions happening. Now, if you're wondering, what's the point here now? Okay, so why did we do this? So okay, why we did this is because OH groups are not good leaving groups. We know that. Okay, so what we just did with the tosylate group is we made it a good leaving group. Okay, so instead of just having to attach chlorine, you can actually attach any kind of a nucleophile, okay? And you can do any kind of a nucleophilic substitutions, okay? Later on, I'm going to give you more examples. I don't have them right now. I will add that to the slide, okay, later. And so you will see that you can actually have a lot of substitution reactions that you can do with this. Now the question is, why is this such a good leaving group? Okay, so fine, you have this tosyl group, but why is it such a good leaving group? So now you have to try to understand is where is the tosyl group coming from? The tosyl group is actually coming from what is called para-toluene sulfonic acid. So if you take away this and you put OH here, this is now TSOH. Okay, this is toluene sulfonic acid. This acid, I want you to just focus here with me a little bit, right here with the sulfonyl groups. This resembles sulfuric acid, right? Sulfuric acid also has sulfur and then oxygens on there. Sulfuric acid is a fairly strong acid. Strong acids give you weak conjugate bases. So which means that if you have a strong acid, it's going to give you a weak conjugate base. That OTS that I wrote right here, that's actually the conjugate base of sulfonic acid. Okay, so that is kind of the backstory of why tosylates and mesylates work like this. Okay, because they are the conjugate bases of strong acids. You don't see that in tosyl chloride. Okay, but tosyl chlorides are actually made from tosyl or sulfonic acids. Okay, that's where it's coming from. And you don't need to know the backstory, but now that you know it, you understand. I'm not just, saying all of these things just to kind of make you remember all of this. It's not that, so all of this has a reason, okay, for it. So tosylates and mesylates are really good because, again, they make OH groups really good leaving groups, okay? Otherwise, alcohol groups are not good leaving groups. OH minus it's terrible as a leaving group. Okay, now here's something to think about, okay, regarding stereochemistry. So I've given you two reactions that can happen. All right, so one was with the PBr3. Remember, you can do substitution directly on the alcohol group. Okay, so then you can get the halide, and that's an SN2 reaction. Okay, and then here is the one, here's the series with paratonyl sulfonyl chloride, okay, TSCl, sorry. So let's look at both of these reactions, okay? And the goal is not to get the chlorides, okay, in there. The goal is, let's say, to get an ether, okay? So this is an ether, which we're going to study anyway, but this is an ether functional group. So this is our final target. So when you take an alcohol, which is R, you treat that with phosphorus tribromide, you end up getting an inversion of stereochemistry because you did SN2 reaction. Now the ethoxide comes in. This is going to be another SN2 reaction. And now you get R. So again, backside attack, right, with SN2 reaction. So you went from R to S to R. Now, you take the same alcohol. Now you treat that with tosyl chloride. When you treat it with tosyl chloride, the stereochemistry is retained because the reaction is happening only on the oxygen. It's not happening on the carbon. It's only happening right here. So which means if you started with R, you're still at R. Now when you bring in the nucleophile and now you do SN2, now you will have inversion of stereochemistry. So now you end up getting S as your product. So depending on stereochemistry, you can either choose the top route or the bottom one, depending on what kind of chirality you want. Now, I do ask you about chirality, okay, when we do these kind of reactions, because this is one of the things about tosylates. It's a characteristic of tosylates is the retention of stereochemistry when you make a tosyl group, okay, and then you have an SN2 going on. So keep in mind, okay, all of this stereochemistry as you are doing these reactions. And I don't have one right now, but I will make a slide of some of the nucleophiles you can use, okay, for doing substitutions. So now let's deal with the last reaction of alcohols, which is the oxidation of alcohol. So you'll remember this scheme that I wrote for you before, where you can take an alcohol and take it to an aldehyde, a carbonyl, or all the way to the acid, which is also a carbonyl, but this is an acid, okay? We've done reductions already because we were synthesizing alcohols. Now we are doing reactions. So we are doing the top portion, the blue one. So to go from an alcohol to the middle, you need a weak oxidizing agent. To go all the way to the acid, you need a strong oxidizing agent. Again, the O here just tells you it's an active oxidation. Where that oxygen is coming from, you don't know yet. Okay, that it could be coming from anywhere. I'm going to tell you that, okay, in just a minute or two. Okay, so this is the top series is what we're doing. Now, what I need to point out here, just like we had a little bit with reductions also, here, if you have a secondary alcohol, then you can oxidize that to ketone. A primary alcohol is given to you right here. So primary alcohol can be oxidized to aldehyde. Secondary alcohols can be oxidized to a ketone. Tertiary alcohols cannot be oxidized. Okay, there is no reaction in there. So this is something to keep in mind. All right, so primary alcohol can go to aldehyde and then all the way to the acid also. Okay, in there. A ketone cannot go to the acid, by the way, okay, because ketones are internal groups, so they will stay inside the two carbons. All right, so carboxylic acids are terminal groups. Okay, let's look at the reagents you're going to use now, okay, for doing any kind of oxidation. So first of all, remember, you need two different kinds of oxidizing agents, a weak one and a strong one. Okay, so here is the weak one. So this weak one is called PCC, pyridinium chlorochromate. That's the structure. You can say PCC. That's an easiest way to use, this name. So you don't have to write pyridinium chlorochromate if you don't want to, but if I write pyridinium chlorochromate, you should know it's PCC. If I give you this structure, you should know it is PCC. Okay, but if you're writing for me, you can write PCC and get away with it. Okay, anyhow, so here is a primary alcohol giving an aldehyde. Here is a secondary alcohol giving a ketone. Okay, so that is how these weak reagents work. For a primary alcohol to go to carboxylic acid all the way to the other side, you need to have a strong oxidizing agent. And the strong oxidizing agent is KMnO4, potassium permanganate. Okay, that's usually a very good oxidizing agent to use. So it will take you all the way to carboxylic acid. Again, remember only primary alcohols. So here is a little bit of a summary in case you are looking for different kinds of reagents or what each alcohol does. So here is the strength of oxidizing agents. The weak one, you have only one, okay, PCC. The strong ones, you can use any of these, okay, it's fine. So you can use chromic acid, potassium permanganate, sodium dichromate, or Jones reagent, which is actually chromate also in sulfuric acid. You can see that this one, this one, all chromates. And chromates actually quite toxic, So KMnO4 is preferred, but again, KMnO4 is messy, but chromate is toxic, like, pick your evil choice here. Anyhow, and then here, this is a summary of what happens with oxidations of alcohol. So primary to give you aldehyde, you need weak, such and such. Okay, so that's your little summary here. Here are some examples of what you can do. So here, if you have a secondary alcohol and a primary alcohol, and you choose PCC, then you oxidize both. If you use KMnO4, you will oxidize both. But when you do PCC, it doesn't go to acid. This goes to aldehyde. Okay. KMnO4 will take the primary alcohol all the way to the acid. You still get a ketone over here. Okay. So then here also you have some variety of oxidizing agents. I added a little bit of interesting thing here. So this is an alkene, because alkenes also react with KMnO4, and I don't want you to forget that. Okay, so if you have this kind of an alcohol with an alkene also in there, you treat that with PCC, which is the weak oxidizing agent, you get an aldehyde. Alkene is still fine. But if you have KMnO4 cold, room temperature, then you oxidize the alcohol to the acid, but you also form a diol, okay, at the alkene, so you have to be careful. If you treat this compound with hot KMnO4, then you'll end up cleaving the double bond, okay? So you might remember that from your alkene reactions. So you end up cleaving this, and if you cleave this, you end up getting an acid, and an acid. So really, we're just full of acids now. Okay, so that's what we end up getting. So you have to be careful in your choice of reagents. Okay, so I gave the explanations over here, but be careful. And finally, we'll talk about qualitative analysis. So qual analysis is when you see some sort of a physical change, precipitate formation, color change, gas formation, something like this with any kind of a chemical test. So here we're doing the chemical test for alcohol. So there are three kinds of alcohols: primary, secondary, tertiary. So there are two tests that we can do with alcohols. Okay, one is oxidation and the other one is substitution, which is on the next slide. So in the case of oxidation, what you can tell about the primary, secondary, and tertiary alcohols is that primary alcohols, as we know, get oxidized, secondary do as well. Tertiary alcohols do not get oxidized. Okay, so if you want to just find out if you have a tertiary alcohol or not, then this is a good test to do. So what is the test? The test is with chromium oxide, and you can use Jones reagent or something like that. So any kind of chromium will work. So chromium here is 6 plus. Okay, we have 3 oxygens, so chromium is 6 plus, which is an orange solution. That orange solution, once it oxidizes, well, not the orange solution, the chromium, once it oxidizes the alcohol, it itself will be reduced because it's a redox reaction. So once it gets reduced, it gives Cr3 plus, which is sort of a green-blue solution. So the qual test analysis here is just of a color change. Okay, so a primary alcohol, which the alcohols themselves are not colored. Okay, remember that they are, colorless usually. But when you add the chromic acid, which is orange in color, so when you add that to a primary alcohol, the result will be a blue solution, which will have the oxidized alcohol and then the chromium ion, okay, in there. Same thing happens with secondary, but tertiary don't give any sort of a reaction, okay, because they don't oxidize. So it's a good way to tell whether you have an alcohol, first of all, and second, if you have a tertiary alcohol or not. Now, if you are testing just for alcohols, then this is not a very good test to do, because even though a tertiary alcohol is an alcohol, it is not giving you a positive. I hope you see what I mean. Now you can do the same kind of test with potassium permanganate also, because potassium permanganate can also oxidize alcohols. Again, primary and secondary it can oxidize. Tertiaries don't get oxidized, okay? So if you add potassium permanganate, which is actually a purple solution, the manganate ion gets reduced to MnO2, and then manganese dioxide is actually a brown precipitate. Okay, so that's what happens with primary and secondary alcohols, so not with tertiary again, okay, because tertiary don't get oxidized. And here's the Lucas test. The Lucas test is when you take an alcohol, treat it with zinc chloride in presence of concentrated HCl. Oops, I have H2SO4, it should be HCl. So if you treat it with HCl, then you end up getting an alkyl halide. So here is a typical reaction, okay, for the Lucas test. So what happens in this case, we know that since we are working with concentrated HCl, then the mechanism here is going to be SN1, which is favored by a tertiary cation, right? So tertiary cations are favored, which means that tertiary alcohols will give you a positive test. So what is that positive test? That positive test is you kind of get a cloudiness, sort of a white precipitate, with the as a result of the alkyl halide. So if you have a tertiary alcohol, then you can see that cloudiness happening immediately. For secondary alcohols, it takes a little bit slower time, maybe 15 minutes or so or more. And then primary alcohols, forget it, okay? Because primary alcohols will not form any precipitate, because primary alcohols do not undergo SN1 mechanisms, okay? So that's a qual test for primary, secondary, tertiary alcohols, more like tertiary, right? So we were not able to do tertiary alcohol test with potassium permanganate or the chromic acid, because tertiary alcohols don't get oxidized. But this one is a good one to do for tertiary alcohols then, okay? And so I think that's it as far as the reactions are concerned.